Okay, I'm going to demonstrate execution of red-black tree insert. But first, we just click this little exec button, and we see a random tree pop up with a random value to add. And we see that there's 2 points of execution so far because we have the beginning of the procedure, which is just nothing's happened yet. And if we click on the next one, we go to the insert bin instruction, and we see that n is inserted, 76 is inserted at the bottom of this tree below 63, and then the n is assigned the n variable, which is used up here. So let's go ahead and build our tree really quick. Define our program. We're just going to do what we usually do. We generalize all the ones to k, and then do a switch on the parent of n, make that switch more complete. You can already see that we're adding lines here, lines of execution. So this v equals 76 goes to this add height here, and then it falls into the switch and stops at this node is black case. So let's go ahead and write this case out, which is basically just compress and return. So this one's already done. And you can see here it goes generalize, and then we add the p variable because that's used to capture the black node parent. And notice there's a minus sign here, which says that the axes are flipped because here n is on the right and here n is on the left. So we reflect that in this representation by putting a minus after the p. Okay, so let's go ahead and do the rest of the cases here. This is black. Let's do a compare axes here. Rotate this guy up. Black, red, compress, return. Rotate this one up, then do a go to the previous case. Red, black, black, compress, compress. Go to the top of the loop. Okay, so now we've completely, empty case too, sorry. We've completely defined our insert function. So let's go ahead and, so this concrete example only goes through the really simple case here. So let's go find a case that's a little bit more complicated. So we hit the exec button and we get a new test case. This one's for V46. This one's more interesting because it's adding a red node underneath a red node, which means we'll have to rebalance the tree. So we go and we look, and we fall into the parent is red and the grandparent is black, and then we have an uncle that's red. Okay, and here we say p is flipped. We have the uncle, we have n and g, but of course it doesn't really matter that p is flipped here because for this logic we're just going to recurse up. So we flip the colors. Parent and uncle become black and the grandparent becomes red, and then we compress the two, the parent and uncle subtrees, and then we just go back to the top of the loop. So you can see now g becomes n. I'm sorry, yeah, g is the g, whatever was in g is now in an n, and then we start this loop over again, go through and do this again, and we actually have to go through and do the same thing again. And then, our grandparent is red again, and then we go back, and then we have a black parent, and we can stop. So let's find something a little more interesting that has a rotation in it. Let's see. Oops, sorry, didn't need to do that. I can tell the rotations are actually kind of rare in the randomized input, at least. So there we go. Okay, we have a rotation. All right, so we now are inserting this 174 into the bottom of the tree. It's to the right child of 157. Again, we do our switch. P is flipped. Then we do our case analysis. We have a black child. We don't have a red uncle anymore, so we're not going to fall into the same path that we were falling into before. Instead, we have, Instead, we have this p is flipped, and we have n down here. G and P have different axes. P is flipped and G is not. So when we do this compare axes, we'll run into the false path, and then P will be flipped, so that it won't be flipped anymore. I mean, P's axis will be reversed, so it won't be flipped anymore. So you see now that P becomes P minus goes to P, and then we look at the shape, and it actually looks just like the shape up here in our abstract representation. We do the rotate. Sorry, I have to do the rotate here. And we do the rotate, and the nodes are physically rotated, and you can see the shape matches what the concrete shape matches the abstract shape up here. Okay, and then we do our goto, which is basically we're going to relabel P and N and swap them, and go back to the true case rotation, flip some colors, do the true case rotation, and then we're going to physically rotate NGP, the same shape. It's being repeated. Flip some colors, and then compress and return. Okay, and that's really about it, Mike. So I don't think the concrete representation of the redback tree is very useful when writing this code, because the abstract representation has everything that we need. I'm just kind of showing it here to sort of illustrate what's really going on between the abstract representation and the concrete representation. If you read this as code, you can sort of imagine that, yeah, this is how this code is supposed to execute. All right, thank you.